From the distributed load, we have a force of 10 kips, a support reaction at A support reaction at B, and a moment of 30 kips per feet. From these equations, we get A to equal 9.5 and B, that's By equals 0.5 kips.
There are two ways to find shear moment diagrams. One is to do it visually by looking at the applied forces and moments on the beam, or analytically by dividing the beam into sections and finding the internal shear and moment equations. The first thing we're going to do is look at the shear diagrams. So we look at the applied forces. We start at x equals 0. Because we have an applied distributed load, as we go across the beam, the load will gradually get larger, which means that the line on the shear diagram will be at an angle, a sloped angle. Because the force is going down, that means that's at a negative angle. We know that the largest shear force from 0 to 5 is going to be 5 times the distributed load of 2. So we draw the negative slope, and it goes to -10 because it's in the negative direction. The next force we look at as we move across the beam is at x equals 5, which is A of 9.5. And because it's in the positive direction, that means we go up on the shear diagram, about 9.5 kips, which brings us to -0.5 on the diagram. Going across the beam, the next force we look at is B equals 0.5. And because there are no more distributed loads or forces between x equals 5 and x equals 10, that means that it's going to be a straight line on the diagram. Because B is in the positive 0.5 direction, that means that it's going to go up on the diagram 0.5, which leaves the diagram at 0. And this is good because the beam is in equilibrium, so that means the forces have to be equal to 0. The next thing we're going to do is find the moment diagram, and we use this equation that the moment is equal to the integral of V, which means that the moment is equal to the area under the curve of V. So we look at the shear diagram, and we know that from 0 to x, it's linear, which means that the moment is going to be parabolic from 0 to x. And we know that the area under the curve of V is -25 because it's below the x-axis, which means that the curve of the moment diagram is going to be parabolic, ending at -25. The next section is from x equals to 5 to x equals 10. We know that the function of the moment diagram is going to be linear because V is constant at the point. So we know that it's going to end up 5 times 0.5 away from where we left off. That means the moment diagram is going to end up at -27.5. Next is the applied moment at x equals 10. And it's a negative moment on the beam, but because the moment diagram shows internal forces, this makes the internal moment a positive 30, which shoots up to 2.5 on the graph. The next applied moment we look at is from the force of B equals 0.5. This means that we look at the area under the curve from x equals 10 to x equals 15. Because it's constant on the shear diagram, that means it's going to be linear on the moment diagram, which again brings us back to equilibrium.
For the analytical method, we cut the beam into sections, with the first section ending just before 5. We start by writing down all of our forces. The first force we get to is the distributed load of 2 times the distance, which is x, in the negative direction. And then we move along without any more forces until we get to the shear, which is also in the negative direction. After solving for V, you get V equals -2x. Next we look for moments. And we have the force of 2x times the distance, which is half the distance, so it's x over 2. And then we keep going until we get to the moment, and it is also in positive direction. After solving for m, we get -x squared. The next section we are doing is from 5 to 10, and going with x in the positive direction that way, our first force that we come to is the distributed load, which is 2 times 5 in the negative direction. The next force we come to is at A, and A equals to 9.5 in the positive direction. Moving along, we don't get to another force until the shear, and it is in the negative direction. After solving for V, you get V is equal to negative 0.5. Moving along to the internal moment on the beam, the first force we come to, the next moment we come to is created by A, which is in the negative direction. We don't come to another moment until the very end, and it's just M. After solving for M, we get negative 0.5x minus 22.5. The last section of the beam is from 10 to 15. Start by starting at x equals 0 and moving across with your first force being 2 times 5 in the negative direction plus 9.5, and then you don't have another force until your shear force in the negative direction. You get V equals negative 0.5. Finding the moment in the beam, the first force you come to is you get negative 0.5x plus 7.5. By using the sections method and finding the shear moment equations for each interval, we were able to find the shear moment diagram for the beam, which equals the visual method that we used earlier.
From these diagrams, we can determine the maximum shear and the maximum moment, and we can plug them into our equations over here and determine our max shear stress and our maximum normal stress. This is especially important when building because we have to take into account the maximum stresses that the beam can withstand. With different structures comes different stresses, and we can use these diagrams to determine the maximum stresses at each point on the beam.
No, does not have the leg. And Chris Davis takes it in the back of the end zone. He'll run it out to the 10, 15, 20, 25, 30, 35, 40, 45, 50, 45. There goes Davis. Oh my God! Davis is going to run it all the way back. Auburn's going to win the football game. Auburn's going to win the football game.